Waidusmacademy. Today we'll be looking at half-life in radioactive decay, in radiation. Okay, so today we're looking at half-life. So I think after half-life, we just do uses and dangers of radiation. That's it. In another class, we take uses and the dangers of radiation. We'll combine it in one class, and that will be all for this chapter. I think that will be all for the normal physics, except the new one, the new topic they introduced. That's the only thing that is remaining after this chapter. So this chapter only one class. We can even finish it tomorrow. This chapter. Okay, so without much ado, let's begin. Half-life. What is half-life? Okay, what is half-life? Before we begin, let's listen to this tutorial for half-life.
We'll be looking at half-life. Half-life is the property of radioactive isotopes. It is the time it takes for half of the radioactive nuclei in a sample to decay. An alternative definition is the time it takes for the activity or count rate of a sample to decrease by half. These blue circles on the right represent a sample of radioactive parent nuclei. After one half-life passes, half of these have decayed to the daughter nucleus. After another half-life passes, half of the remaining parent nuclei decay again, and so on. The half-life of a particular radioactive isotope is independent of the sample size. This is caused by the random nature of radioactive decay. Changes in the activity of a sample over time can be plotted on a graph. These graphs can tell us the half-life of a sample. The y-axis of these graphs may show the number of radioactive nuclei or the activity of the source in counts per second. Here, 8,000 nuclei have halved to 4,000 over 4 years. This means the half-life of the source is 4 years. Remember, half-life is independent of sample size, so it will take another 4 years for those 4,000 nuclei to drop to 2,000. If asked to draw one of these graphs in an exam, make sure your line approaches the x-axis, but never touches it. Okay, let's take a look at a worked example. This is a common half-life question in exams. A very old sample of wood contains 1.0 times 10 to the 8 carbon-14 atoms. When the sample was new, it contained 8.0 times 10 to the 8 carbon-14 atoms. The half-life of carbon-14 is 5,700 years, and we are asked to estimate the age of the sample of wood. It's always a good idea to list or highlight the important information in the question. We start off with 8.0 times 10 to the 8 carbon-14 nuclei. We end up with 1.0 times 10 to the 8. Carbon-14's half-life is 5,700 years, and the command word is estimate. This question is worth 3 marks. We want to start off by finding out how many times we need to halve our initial number of nuclei to reach our final number. So, first we halve 8.0 times 10 to the 8, giving us 4.0 times 10 to the 8. This is not our final number of nuclei, so we halve again. This is still not our final number of nuclei, so let's halve one more time. Now, we've reached our final number of active nuclei from the question, 1.0 times 10 to the 8. We have halved the number of carbon-14 atoms 3 times. This means that 3 half-lives have passed, which is the first mark. Next, we need to calculate how long this has taken. This is a nice, simple calculation. If 3 half-lives have passed since the sample was new, its age must be 3 times the half-life of carbon-14. And the final mark is for writing the answer with the correct units. That's 17,100 years. With questions like these, a common error is to think that 8 half-lives have passed, because that's how many times the final number of nuclei fits in the initial number. But you need to remember that we are halving the number of nuclei each time. The clue is in the name, half-life. Another common type of half-life exam question involves graphs. Here, we are asked to use the graph to determine the half-life of the source for 2 marks. We'll start off by finding half of the initial activity. A0 is 6 squares up the y-axis, so A0 over 2 will be 3 squares up the y-axis. We then need to use the graph to read the time at which activity reaches half its initial value. We've already gained a mark. This is for drawing a pair of lines on the graph. Remember, you are asked to use the graph, so make sure you annotate it. Next, we read the time on the x-axis and determine the time taken for the activity to half, which is 7.5 years. This is the definition of half-life, so we can now say that the half-life is 7.5 years for the second mark. Stopping here in your exam would be unwise when we can do the same thing again to double-check our first answer. Halve the activity again and read the time taken to go from A0 over 2, A0 over 4 using the graph. This is also 7.5 years, confirming our answer. That's 2 guaranteed marks in your exam. To summarize this video, our definition of half-life is the time taken for half the active nuclei in a sample to decay. Half-life graphs show how the number of active nuclei changes, and we can use them to determine the half-life of a sample. Don't forget to check out all our other fantastic revision resources at Save My Exams.
Okay. Now let's quickly, we listen to the tutorial. Let's quickly analyze. Today's topic is half-life, like we said. Half-life is the time taking. So first of all, you must know its time. When we say half-life, it's time taking for half the radioactive substance, or the half of the radioactive sample, or the activity, okay, to decay. The half it takes for the activity to decrease to half. The time it takes for the activity to decrease to half, or the time it takes for the radioactive substance to decay, or the time it takes for the radioactive sample to decay. So half-life is basically the time. It's about time. How long it takes, the time it takes for a sample of radioactive substance to decay or to decrease to half of the original number. Is that okay? So now let's take a look at the basic things that we're supposed to look at. We say it's very possible to know when a particular unstable nuclei will decay. When it will happen, it's almost impossible to tell, but we can tell the rate at which this activity or sample decreases. We can tell the rate at which it will happen, the rate, okay? And that is what we call the half-life, okay? The time taken for half of the radioactive substance or sample to decay, okay? So that's what we call the half-life. Now we can show this in a graph. From the graph perspective, if you're given a graph and they're asking you to calculate the half-life, whatever number is here, we presume that the background radiation has been deducted. If they say the number here includes the background radiation, you have to subtract the background radiation from the activity here. Here, it's always a plot of activity against time. Okay, when you take a look at the graph, we always plot activity. Activity in half-life, activity is measured with Becquerel. The unit is Becquerel, BQ. The symbol is capital B, small letter Q. Okay, the unit for activity in half-life is Becquerel. The unit of activity, because we always plot activity against time. In half-life, we plot the activity of the radioactive sample against time. We plot the activity of the radioactive sample against time. So this activity is always plotted against time. And when you do that, then you get the half-life. You'll be able to calculate the half-life activity. Okay? So the unit of activity in this regard is what? The unit of activity is called Becquerel. Becquerel. And the symbol is BQ. The symbol is BQ. The symbol is capital B, small q. Okay? Remember this. So this activity is always plotted against time. The activity is always plotted against time. Okay, in physics. So now let's say that. Let's say you have a graph here. let's say this is our graph. Okay, so we always, this axis, the y-axis, this is our y-axis. This y-axis is the activity. Here we have the activity. Here we have the activity. Okay, I just write A. And then we plot against time. Here's the time axis. Here's the time axis. Okay, so, you know, we make sure it never touches the x-axis. Okay, this is it. We make sure it never touches the x-axis, which is the time axis. Okay, this is the activity axis. So what we do, we always see the number that is written here. If here is 8,000, if the activity here is 8,000, if it's 8,000, and they ask you to calculate the half-life. So what you do is to have this value, okay, without, if background radiation is negligible. So 8,000 divided by 2, you get 4,000. You know, naturally 4,000 will be halfway here. 4,000 will be halfway here. Right? 400 will be here. 4,000 will be here. So what you do is to always bring this one, let's say, from half of the value. After you have this value, so what you do is to come to half of the value, trace it to the curve, and bring it down. Once you get to the curve, then bring it down to the x-axis, the time axis. So whatever value you get there, let's take a look at it from our material. So the first half, like in this case, they didn't give us value on the y-axis, the activity axis. Remember I said we always plot activity on the y-axis and plot the time on the x-axis. Now activity is the sample, the number of the sample. That's what we call activity. The number of sample in the radioactive nucleus that will eventually decay or not decay. Okay, the one that will decay or the one that will remain. So that's activity. The unit is becquerel, BQ. Okay, can be asked in multiple choice. The unit of activity is becquerel, which is BQ. Okay, so now this activity, in this case, they ask you to calculate the half-life. Okay, they ask you to calculate half-life. What you do, you count how many boxes. If they did give you a number, 1, 2, 3, 4. There are 4. So if you divide 4 boxes by 2, you get 2 boxes. So means if A is A naught, so half of it will be A naught over 2. So you trace this one to the curve and trace it down. The time, whatever time is here, if it's 2 years, 5 years, whatever time is here, 10 years, 500 years, whatever time is here is the half-life of this radioactive isotope. It will be the half-life of this radioactive isotope. Okay, so that's that. Now let's take a look at the number of half-lives and with relation to the proportion of isotope remaining. What is remaining? You know, every half-life, half of it decay, half of it remains. Every half-life, if you move another one half-life, half of it will decay, half of it will remain. So in the first half-life, if the half-life is 1, what is remaining, if you want to calculate it, you divide it by 2, 1 all over 2. Either you say divide by 2 or you say multiply by 1 all over 2. You multiply the original radioactivity, let's say 8 times 10 to the power of 8, multiply it by 2 or divide it by 2. Multiply it by half, not multiply by 2, multiply by half if you are multiplying, or just say divide by 2. You will get what remains. Half of it is what will remain and half of it is what decay. If 2 half-life have passed, if you want to find what is remaining, you say the proportion of the radioactive sample that is remaining, you just multiply the original activity by 1 all over 4 or divide by 4, whichever way you say it's the same thing. So you multiply by 1 over 4 or you divide by 4. If 3 half-life have passed, if you want to find the sample that is remaining, the sample of radioactivity that is radioactive substance that is remaining, you just multiply by 1 all over 8 or divide by 8, you get what is remaining. Because what is remaining, it's 1 over 8 of what the original one was. If 4 half-life have passed, You multiply by 1 all over 6, you get that. Okay? So that's it. Here is a question which we go to listen to and or we just do it on our own. A detector close to a radioactive source produces a count rate of 1,600 counts per second. After 32 hours, see, this is the count rate. Okay? This is the activity count. It gives us 1,600 counts per second. After 32 hours, the count rate has fallen to 100 counts per second. After 32 hours, the count rate has fallen to 100 counts per second. It has reduced from 1,600 to 100. Assuming that the background radiation has already been taken into account, they've treated background radiation, we don't need to do anything about it. Calculate the half-life of the source. So work out how many half-life that has occurred in 32 hours. Okay, in 32 hours. How many half-life? So what we do is we write the original source, right, which is 1,600. In the first half-life, you divide this by 2. 800 will remain, right? That's first half-life. So because they say we should work out how many half-lives, meaning not one half-life, how many half-lives. So what we do, we come to, although our body is not friendly, it's not friendly. So we write, the first count is 1,600. One thousand 600. That's the first count. Guys, the board is lagging. 1,600. I will even use a dot for 0. 1,600. So let's use dot for 0 if it's not writing. Okay, so if you want the first half-life, you divide this number by 2, right? The first half-life, you divide this number by 2. Okay, it's not right. Let's just go to the material. You divide the number by 2. In the first half-life, you divide this number 1,600 by 2. What will remain? What remains and what decays? 800 will decay, 800 will remain. That's in first half-life, so you have 800. Second half-life, you divide this again by 2, you get 400. In the third half-life, you divide this again by 2. That's in the first half-life, we divide by 2, 800. Second half-life, we divide this one by 2, we get 400. That's second half-life. Third half-life, we divide 400 by 2, we get 200. Fourth half-life, you divide 200 by 2, you get 100. So there are 4 half-lives. So in this case, there are 4 half-lives. Okay, after 32 hours, there are 4 half-lives that have passed. Okay, so that's that for this question. Let's take a look at the tutorial.
Here's a question for us to look at, and let's start by reading through the question carefully and get a clear understanding of what we have to do. A detector close to a radioactive source produces a count rate of 1,600 counts per second. After 32 hours, the count rate has fallen to 100 counts per second. Assuming that the background radiation has already been taken into account, calculate the half-life of the source. So this is a question relating to half-life. Let's just make sure we understand exactly what's going on here. So we have to calculate the half-life, and there's nothing else particularly worrisome in the question. We've got an initial count rate, we've got a count rate after a certain period of time. So the first and most important thing is to remember what the half-life of a radioactive source is. So just as a reminder, here's a screen grab from our theory, and here we go. The half-life of an isotope is the time taken for the activity or the number of nuclei to drop to half its initial value. So we're starting off with 1600 and we're ending up at 100. So we need to know how long does it take to drop to half its initial value. So the first thing we're going to do is we're going to try and work out how many half-lives have occurred over this 32-hour period. So that's the first step there. Now, in answering this question, what I've done is I've prepared a table. You can do this very simply on a calculator, or you can actually even do this one in your head. It's not particularly difficult arithmetic. But what I've done is I've halved the activity or the count rate. I've just kept on halving it until I get back to 100. So let me just show you what that looks like. So there I've just listed the half-lives. So we start off at 1600, that's what was given over there. I halve it, so my first half-life will go from 1600 to 800. I then make this my second half-life and I halve it, and so I've carried on until I end up with a count rate of 100 counts per second. What I can see from the table is that this takes 4 half-lives. So to get from 1600 to 100 requires 4 half-lives. And that I've captured in my answer window over there. So the source undergoes 4 half-lives in 32 hours. So we then can work out that each one of those half-lives takes 8 hours to complete. And that's the final answer to this question. The half-life of this particular radioactive source is 8 hours.
Yeah, why is the half-life 8 hours? Because in the end, you are given 32 hours. And there are 4 half-lives. So to get the hours, what it takes, the time it takes, you divide 32 by 4 half-lives that you have you've calculated. Okay? So you get 8 hours. 32 hours divided by the 4 half-lives you calculated, you get the 8 hours. Now let's take a look at half-life from a graph. We say in the graph, we always plot the activity on the y-axis and plot the time on the x-axis. We plot the time on the x-axis. And then in half-life, we always take care of the background radiation. Background radiations are the radiations that are always present in your radiation. So they're always there. Okay, so we always subtract them from the original count rates that we measure from the radioactive decay. We subtract the background radiation. So we assume this line as our background radiation that is always present in a radioactive decay. Okay, so that's that. This is the graph. Half-life is exponential decay. Okay, the curve plotting activity against time is an exponential decay curve. It's an exponential decay curve. Okay, so here if you look at this, how many boxes? 1, 2, 3, 4, 5. So if you want the half-life, 5 divided by 2, you get 2.5. So I count 1, 2, 2.5 is here. So I draw, where I meet the curve, I draw it down. So here will be my first half-life. Whatever time is here, will be my first half-life. Okay, to double check that, the remaining 2.5 divided by 2, you get 1.25. So one box, 1.25 will be somewhere here. You draw it, drag it down, it reaches here, you bring it down, you see it's same time length. So you verify the second time, the second half-life. Okay, now let's take a look at a pure example from here. A good example from here. The radioactive technetium is used extensively in medicine. The graph below shows how many activity of the sample varies with time. How many activities of the sample varies with time. You can see here the activity in Becquerel, BQ. I told you activities in Becquerel, BQ. So any number you see here is times 10 to the power of 7. That's why they put this one here. So if you see 8, it means 8 times 10 to the power of 7. If you see 7, it means 7 times 10 to the power of 7. So these are in times 10 to the power of 7. Is that okay? And these are in hours. The time is in hours. So if you want to find the half-life of this graph, you say 8 times 10 to the power of 7 divided by 2, you get 4. Meaning we're going to come here, okay, and draw it to the curve and drag it down 6 hours. So the half-life for half of the radioactive, the time taking for half of this radioactive substance to decay is 6 hours. The time taking for half of this one to decay is what? Is 6 hours. Is what? 6 hours. Okay? Now, if you want to verify again, this one you divide by 2. 4 divided by 2, you get 2. So you also trace 2 to the curve. It comes to 12. You see, from 6 to 12 is another 6 hours. From here, from the first half-life to the second half-life is another 6 hours. So it means every time the half-life will be 6 hours. So if you divide 2 by 2, you get 1. So if you trace 1 to the curve, you arrive at 18. If you trace it down, 18. So from 12 to 18 is another 6 hours. From 12 here to 18 is another 6 hours. So meaning half-life is 6. So from the first 6 hours, you get the first half-life. Second 6 hours, which by 12 hours, you get second half-life. By 18 hours, you get third half-life. So by 24, because if you divide this one by 2, you get 0.5. If you trace 0.5 to here, you would have reached 24. So by 24, you get 4 half-lives. Okay, so that's how to calculate half-life from graph in the exam. Okay, but if they tell you that background radiation added to it, you subtract the background radiation from this before you start to divide. Well, let's say the background radiation is 2 or is 1. Subtract 1 from here, it becomes 7. You divide 7 by 2, you get to 3.5. That's when you get your half-life. 3.5 would have given us the half-life. Okay, if the background radiation was inclusive of this. Okay, so that's it. See, this is what I have explained. So if they ask you to calculate the half-life, 8 times 10 to the power of 7 divided by 2, you get 4 times 10 to the power of 7. So you trace this 4 to the curve and you bring it down. That is your first half-life. Half-life is T half. You know it's time taking, so half time. Half time for half of the radioactive source to decay. Okay, so that's the first half-life. So the first half-life is 6 hours. And we say logically it's always better to double check. After doing the first one, do the second one to see whether you get another 6 hours from here. From here, if you divide this 4 by 2, you get 2. You trace 2 to the curve and trace it down, you get 12 hours, which means from this to this is another 6 hours. Okay, so that's how you double check if you are right. Okay, so that's it. Here are the steps. In the diagram above, the initial activity is 8 times 10 to the power of 7 becquerel. Now the time taken to decrease to half is 6 hours. Okay, by dividing this one by 2, you get 4 times 10 to the power of 7, and you trace the 4 times 10 to the power of 7 to the curve, and you trace it down, you get 6 hours. So it's 6 hours. Every time there will be 6 hours. In another 6 hours, there will be another half-life. What it means, in another 6 hours, half of this one will decay again. Half of it will decay in another 6 hours. Every 6 hours, half of the original activity or sample of the radioactive isotope will decay. Half of it will decay. Every 6 hours, half of it will decay. Now let's take a look at another example that does not involve graph in the exam. So a particular radioactive sample contains 2 million undecayed atoms. 2 million undecayed atoms. After a year, there is only 500 atoms of all decay left, right? Only 500,000 atoms left undecayed. 2 million after 1 year, only 500,000 left. Mean 1.5 million has decayed, right? What is the half-life of this material? Now, half-life, you take the original million, 2 million, write 2 million out. Okay? Half-life is the time taken for half of this to decay. So you divide 2 million by 2, you get 1 million. So in 1 million atom, that will be one first half-life. Okay? Because once you divide this by 2, you get 1 million atoms. So that's the first half-life. First half-life is 1 million. You do it again, second time. 1 million now, divide by 2, you get 500,000. That's your second half-life. So there are 2 half-lives. In this one, to reduce from 2 million to 500,000 is 2 half-lives. It takes 2 half-lives. To reduce from 2 million atoms to 500,000 atoms, it takes 2 half-lives. Is that okay? That's not the end of it. What's the age or how long? What is the half-life of the material? Half-life is 2, right? Half-life is 2. So remember, it's 1 year. They've given us. They told us it's 1 year period. So 1 year divided by 2 will be the 500,000, right? So what is the time? Time period is 1 year, right? The number of half-life is 2. We have only 2 half-life. So we divide 1 year by this number of half-life. We divide this time by the number of half-life. We divide this time by the number of half-life. T half. Time is 1 year. They've given us 1 year in the question. Is it after 1 year, there's only 500,000 atoms left. So after 1 year, so what is the half-life of the material? Half-life is 2, but we need to tell the time it takes. So after 1 year, there's only half. So we say 1 year divided by 2 is 6 months. So 6 months is the time it takes for half of it to remain and half of it to go. So that's all we have for today. These are the similar exam questions we have, including the 2 questions or 4 questions from the tutorial and the 2 we looked at from without the tutorial. These are all the exam questions that you'll be asking the half-life. You must know how to define half-life. Half-life is the time. Half-life is the time taken for half of the radioactive sample to decay. And then from the graph, if you're giving a graph curve, and whatever is the highest number, and if they tell you background radiation is already taken care of, meaning you don't have to do anything about background radiation, you take the value here, you divide it by 2, you get 4. If here was 16, the half value would have been 8. So here is 8, you divide by 2, you get 4. Trace this 4 to the curve. Wherever I touch the curve, trace it down. That is the time for the first half-life. That's the time. And half-life is T half. We write T half. T half is the first half-life. Okay? You can double check by dividing this one by 2. Divide this again by 2, you get 2. Trace 2 to the curve. Where it means trace it down. That's 12. So from here to here is another 6 hours. So that's how to verify that. Every 6 hours, there is an half-life. There is half-life. Every 6 hours, there is half-life. So you need to know how to do. These are simple exam questions that you're going to come across. Okay, then if you are given a decay substance in exam and they ask you to tell the age or the time, after you calculate the year they gave you, you divide by the number of half-lives. After you have calculated, you've gotten your half-life. If your half-life is 2 and they give you, they say it takes 6 years, for example, like this question, or it takes 1 year. This question, say it took 1 year. The sample was 2 million atoms, right? We've done that. We were able to calculate our half-life. Now, if you want to know the time, the real time it takes, they say after 1 year, after a year. So this 1 year, you have to divide it by the half-life. Divide it by the half-life. There are 2 half-lives. Okay, you must calculate all the half-life before the original or decay nuclei decay to the new sample. So you calculate all the half-life. If there are 8 half-life, you have to divide 1 year by 8. If there are 4 half-life, you have to divide 1 year by 4. So 1 year divided by 4 would have been 3 months. So it would have been 3 months. Every 3 months, first half-life will have occurred. But in this case, there are 2 half-lives. First half-life, second half-life. First half-life, 2 million decay to 1 million. Second half-life, 1 million decay to 500,000. Remember they say it decayed to 500, only 500,000 was not remaining. So there are 2 half-lives. So the 1 year divided by 2, you get 6 months. That's you get half, which is 6 months. Half a year is 6 months. So every 6 months, one half-life will occur. That's how to calculate this type of question. So these are the type of questions you only find in your exam for Cambridge Igcse. Is that okay? So we come to the end of of this chapter. I told you half-life is a plot of activity. Activity, the unit is Becquerel, and the plot of activity against time. Okay, the plot of activity against time. Okay, so that's how we got the curve for half-life. Is that okay? Thank you for joining us.